Okay, so on page 2, I'm asking you to write a density function for a random variable normally distributed with mu and standard deviation squared. I want you to write the density function fx. At the same time, I want you to write another random variable z with normal distributed with mean 0 and standard deviation of 1. Okay, what's the fx will be for that? Let's say z. Well, it's too complex. Just still use x for that. Okay. Alright, so have a think about that. We have 1 over, okay, 1 over what? Sigma square root of 2 pi. Okay, that's always there. And we have exponential of negative a half x minus mu divided by standard deviation, and then square for that. And we will have, if it's a 0, 1 distribution for normal, we'll have 1 over square root 2 pi times exponential negative a half x squared. X squared. Okay, mu is 0, so x squared. Okay, that's the two different functions. And let's have a look. It's over there. Okay, it's over there. Okay, let's have a look what the question is asking. What is the transformation applied to the standard normal function to a graph of the distribution with mu and standard deviation? So this is a transformation thing. In original function will be y equals to 1 over that e negative half x squared. And I want that to be transferred to y dash equals to 1 over sigma root 2 pi e negative a half x dash minus mu over sigma squared. Okay, it's asking how this can be transferred to that. Okay, so what we'll have is square root 2 pi y equals to e negative half x squared. So exponential negative half something squared is the model. So leave that on the right hand side only. And it's mapping to sigma root 2 pi y dash equals to e negative half x dash minus mu divided by sigma squared. Okay, so overall what I will have is root 2 pi y equals to sigma root 2 pi y dash equals to 1 over sigma y. Okay, that's on the y side. And on the x side, x equals to x dash minus mu over sigma. X dash will be sigma times x plus mu. Okay, times the sigma and plus the mu. So let's have a think what has been done. I'll say this dilation by a factor of 1 on sigma from x-axis, and dilation by a factor of sigma from y-x-axis. And the last one is translate mu units. Well, it's absolute of mu units to the left or to the right. It doesn't like really given here. If mu is less than 0, is to the left. If mu is greater than 0, is to the right. So say mu is -2, is moving 2 units to the left. If mu is 3, then it's moving 3 units to the right. So it depends on what is the mu, whether it's moving left or right. If you still remember what we learned last week, Friday, the last exercise about the dilations for the density function. Remember when you have your random variable become ax plus b, you have dilation from x-axis and then compress from the y-axis. If you stretch that way, you make it shorter on that way. If you compress in that way, you get it longer on this way. So you actually need to stretch by 2 ways to make the area still become 1. So this question exactly shows you that. Okay, a dilation for 1 on sigma from the x-axis is actually compressed, pressed this way. Okay, and then a dilation of sigma from the y-axis is stretched this way. So the area will still become a 1 because 1 going this way and 1 going this way. So with the same factor, so it's cancelled each other. The area still maintain the same. And then translation doesn't matter. Okay, move to the left or move to the right, it doesn't matter. So you can shift it. The area will shift the whole thing together. So area won't change. So if you just stretch it this way and compress this way, that's fine. Okay, area won't change. That's exactly what we learned last lesson. Okay, last Friday, what we learned for the chapter 15D or E. Okay, similarly, you can be also asked how this can be transferred from the this one to that one. Okay, this also can have questions asking you how to transfer from this, okay, from this to that. Okay, transfer a complex one to the normal, standard normal one. Okay, you just doing the same thing, just changing the position for your x dash and y dash, and still set up all the random variables. If we want to, okay, I'm not going to do that. You can have a try by yourself. It's exactly the same thing, just the other way around for x dash and y dash. So you set normal will become x dash y dash, and the front one will become the xy. And then still doing the same translation and find x dash y dash to be the subjects. So that's about some transformation. I'm not really seen this type of questions in VCA about this inner study design. So just better let you know about that. Well, it's not really going to ask this transformation, I think, but it's good to know. Okay, I'm going to page 3, and this is a very important concept here. Okay, page 3 is a very important concept. So the whole normal chapter, it depends on this exercise. Okay, it depends on what I'm talking about here. So what the purpose for, like, this is called the standardized normal. So what is a standardized normal? Let's say we have 2 students. We have student A and we have student B. Okay, those 2 students are not in the same school. Okay, it's not in the same school. For student A, she got a SAC mark of 80. Okay, student B only got a SAC mark of 70. But okay, that's the personal result. And then we have school average. Okay, so what is the school average? Okay, I better add another column here. So the school average gives me that for this school, the average is actually 85. Okay, and for this school, the average is actually 65. And then we have standard deviation. Let's just go standard deviation. We calculate the standard deviation as well for school A and school B. So for school A, the standard deviation is a 5. 5 is too large. Let's say a 2. And for school B is 2.5. Okay, that's the standard deviation. Okay, who's doing better? Can you tell, like, really with confidence and give me the reasoning why they actually doing better? Well, I'm telling you as well, the result are, there's a lot of students there, and the result is following a normal curve, like the bell curve. Okay, the result is follow a bell curve. So basically, in school A, we have a bell curve like that, with 85. And then this one got a bell curve here. It will be a lower graph because got a higher standard deviation. The highest point is 1 over sigma root 2 pi. Remember? The larger the standard deviation, the shorter the graph. So got a shorter graph with standard deviation 65 here. So that's the two things. And then the students is actually here for 70, and that student is here for 90. Well, you can't really tell who's actually doing better. So what we want to do is standardize both graphs. Okay, we want to standardize both graphs. What means by standardize? We want to allocate two students on the same scale. Okay, so the same scale will be a normal distribution with mean 0 and standard deviation 1. Okay, I want to put the two students, I find the correct allocation for those two students on the correct scale. Okay, all back to Z normal. Okay, the standard normal, standardized normal distribution with mu 0 and standard deviation 1. So that's why Z normal is a very important graph. Okay, everything will go back to that one, I'll go back to that scale. Okay, let's have a think how we can put this back to 0, 1. So 70, let's have a think about 70 is equivalent to what? The formula we use is this one. If you can see it, is here. X minus mu divided by standard deviation. X minus mu divided by standard deviation. So what we have 80, right? We have the first student is 80. Well, let's put on a Z score. That's a X. And now I want to put on the Z. So X is 80 minus 85. Divide by 2. What I will have here? What I have here? Negative 2.5. Okay, negative 2.5. So on the Z normal, this student is actually at, that's negative 1, that's negative 2, that's negative 3. The student is here. Okay, that's the position for student A. Okay, on the Z normal curve is actually below the average, so it's going to the left of the curve. X minus mu divided by standard deviation will go back to the Z normal curve. And let's have a think about this one. I get 70, and I will subtract my own school's mean value. So 70 minus 65 over 2.5. What I have here? 2, right? So it's 5 divided by 2.5, it's a 2. So student B is actually here. Student B is actually here. Actually, student B is doing so much better compared to student 1. Okay, doing so much better compared to student 1. Because for student B, how many students in front of him is this much? Okay, is this area here? Is this many students in front of student B? But for student A, how many students in front of her? Okay, is all the value to the right of student A. Okay, all of this green area, that's the students ahead of student A. So actually student A's ranking is very low. Student B's ranking is very high. So B is doing so much better after we put that on the same scale and then we compare them. Also, the area for the red area, can you see the red area like in front of B? That area will be exactly the same for this area here, well, this red area here. Okay, it's very important, okay, everyone, please listen carefully. That is the same area. If we talk about on this standard normal distribution, on this normal distribution, left-hand side normal distribution, the area to the right-hand side of 70 will be equivalent to the area to the right of B, which is 2, okay, which is 2, to the right of 2. So this gives you the same area, that gives you the same probability. So if we're talking about the probability, let's say that's the student B, okay, student B. Let's say the B is greater than 70. That is equivalent to say Z is greater than 2. Those two areas are identical. You will have identical area. You have identical probability. So when you're talking about a random normal distribution curve, it is equivalent to you standardize it first. Okay, you standardize it first, and then talk about the standardized graph. Okay, that will be exactly the same. So how do we get this 2? This 2 is, we get it by 70 minus 65 and divide by 2.5. That's how we standardize it. Okay, how we standardize it? We standardize it by use the x minus the mu divided by the standard deviation. Okay, the mu is the own mu and the standard deviation is own standard deviation. We find the standardized value, which is 2. It is equivalent to talk about the point 2 on the standardized normal distribution. Okay, so they are equivalent points. You must understand that. And you must understand why we use standard normal. We use standard normal is because we can't compare two different bell curves. We want to put on the same bell curve to talk about the value. Who is better? Who is faster? Okay? And then after we put that, we will just not look at the original one. We just look at the standardized one. They have the same property, same probability, and same areas. Okay? So that's why we use standardized distribution. So that's what we talk about. So the formula for standardized is x minus mu divided by the standard deviation. Okay, x minus mu divided by the standard deviation. All right. Why we love standardized normal distribution? One is we can compare it. Second is it got the symmetrical properties, and which is good to do the calculation. Okay, it's very easy to do the calculation. Let's have a look at this one. Okay, if I said this greater than z will be 1 minus smaller than z. Okay, that's true for any distribution. And for the second one is like less than z, negative will be 1 minus, well, is the white area here, right? Is so if you have the z, which is the symmetrical point, because 0 is here, and z is the symmetrical point. So this blue shading area will be equivalent to the green shading area. So 1 minus the green area will be same as 1 minus the blue area. Okay, 1 minus the blue area. Okay, so they are equivalent areas. Okay, that gives you the blue area. Okay, less than z is everything to the right hand side of the blue line, and then you have the blue area. This is the green area. Okay, that is the green area. They are equivalent. And for this one, greater than z negative will be less than z. Okay, will be less than z. They are the same as well. They're all excluding the little bit, this little bit here. And in between A and B, okay, in between A and B, will be use the area of B, subtract the area less than A. Okay, use the area of B, well, the whole area here, and subtract the red area here. That will give you the shading area in the middle. That's something really just like you can use your logic to think about it, but like remember that it's symmetrical about x equals to 0. Okay, it's symmetrical about x equals to 0. Okay, we come to the most exciting thing now here. You need to put this on your notes, okay, or if you bring this one, you need to do a really beautiful graph. Okay, you need to really do a beautiful graph here. Well, maybe use your pencil first. What we're talking about here is, remember before we talk about within 2 standard deviation, that's about approximately 95. Okay, approximately 95. And it is very true for normal distribution. Okay, it's perfect in normal distribution. So it's very, very, very close to 95%. Okay, now we are not only talking about 2 standard deviation. We also can talk about 1 standard deviation and 3 standard deviation. Okay, so this is special for only for normal. It's not going to work for other distributions. Only work for normal distribution. 1 standard deviation, 2 standard deviation, 3 standard deviation, they are all special. So what are the special things? Within 1 standard deviation is 68%. With 2 standard deviation, that's 95%. Within 3 standard deviation is 99.7%. Okay, let's just draw 3 standard deviations here. Let's first use a line from the top to here to draw a vertical line. That's the 0. Well, it's not necessary to be the 0. It can be any with any mu. So we have mu here. And trying to find 3 points. We're trying to find 3 points which equal distance. Like I use well, on mine I use 1.5 centimeters, which represents 3 standard deviation. Okay, each standard deviation with the same distance. So that's mu plus sigma, mu minus sigma, and mu plus sigma. And that's mu minus 2 sigma, and mu plus 2 sigma. And then we have mu minus 3 sigma, and mu plus 3 sigma. And I want you to draw vertical lines. To split the area into 8 pieces. Okay, 4 on each side, 8 pieces. Okay, let's make it correct. Okay, I can't still remember all these values. I still need to calculate every time. So that's why I want you to put this on your notes and make sure you can go back and always look at it. We must have a correct one this time, okay? If you make a mistake, all your calculations later will be wrong. Okay, within 1 standard deviation, that is approximately okay, within 1 standard deviation, that's approximately 0.68, right? 0.68 of the area. So it's very easy. You can find out that 0.34 and 0.34 on each side because it's symmetrical. Okay, 0.34 on each side, or I can say that's a 34%. Okay, I can say it's 34%. It doesn't matter. You can leave 0.34. Okay, add up 68. And you also seen that for the last graph, outside the 3 standard deviation is 0.15%. So this area is 0.15%. This area is 0.15%. Okay, that's the 2 easiest one to calculate. next one. Okay, from here to here is a 95%. Okay, it's a 95%. So I will use 0.95 subtract 0.68 to give me 0.27. I will divide that by 2, give me 13.5% on each side again. Okay, 13.5. So I will have 13.5% here and 13.5% here. Okay, and then from here to here, that's the 99.7%. Okay, that's the 99.7%. So I will use 0.997 minus 0.95, divide this value by 2. So we have 2.35%. Okay, 2.35%. So that is 2.35% and 2.35%. Okay, that is the distribution. How it is distributed in between 1 standard deviation and 2 standard deviation, in between 2 standard deviation and 3 standard deviation, in between mu and 1 standard deviation. So it actually gives you all the values. Okay, it gives you all the values. Make sure you get this number correct and make sure it is in your notes. Okay, it is in your notes. Well, it can save you a lot of time. You don't want to do all this calculation again and again. Okay, everyone, finish this graph. Okay, so it gives you the value for every 1 standard deviation. Okay, you can talk for every single standard deviation. So what's the value after 3 standard deviation on one side is 0.15%. So you'll see similar questions later. Let's talk about that for when we meet the questions. Okay, just for now, complete this graph. Okay, complete this graph. Okay, if you finish, just go to example 1 and read about example 1, please. Well, just be careful that this part, and this part, here and here, they are all 1 standard deviation. They are all equivalent. Okay, but for here, that is not 1 standard deviation. Okay, it's as many standard deviation as you like because it's all to infinity. So that's not 1 standard deviation. So I have 3 standard deviation on each side. Okay, 3 standard deviation on each side, and then we are not talking about 4 standard deviation. It's too far away. It's all near the tail. I'll have very, very low probabilities for that. Okay. Have a look at example 1 here, please. It's some transformation questions again, but just have a revise on it. The probability density function of a normal is giving you that. Write down the mu and standard deviation. So mu will be -4 and standard deviation will be 3. What you look at is just this value here. Or you can just take a 3 square root 2 pi for that one as well. Okay, everything will give you the standard deviation and the mu. Okay, everything will give you the standard deviation and the mu. X minus mu, so x minus -4, divide by 3. Okay, state the transformations required to convert a normal to the standard normal. Okay, this is the question. Convert this normal to the standard normal. Okay, let's just do something here first. So y equals to 1 over 3 square root 2 pi, e -½ x plus 4 divided by 3 squared. Y dash will be 1 over square root 2 pi e negative half dash x squared. And we have 3 root 2 pi y equals to e negative a half x plus 4 over 3 squared. And square root 2 pi y dash equals to e negative a half x dash squared. Okay, just do whatever you do for transformations. That's like chapter 4 knowledge. And we have 3 root 2 pi y equals to root 2 pi y dash. Y dash equals to 3y. X dash equals to x plus 4 over 3. I can either say that is x dash equals to a third x plus 3, or I can say that's x dash a third x plus 4 on 3. Well, if you say it's the second last line, it will be translation first and then dilation. Okay, if you expand it, it's dilation first and then translation. Okay, so it's different. If we talk about the dilation, then dilate by a factor of 3 from the x-axis. Then if we talk about dilate by a factor of 1/3 from the y-axis, and then number 3 is translate 4 over 3 to the right. Okay. If you change the order for 2 and 3, you can say translate 4 units to the right first, and then dilation by a factor of 1 or 3. Then, okay. So you can do both ways. You can do both ways, but better follow the DRT order. So dilation, reflection, and translation. So this is following the DRT order. So 3 from x and a third from y, and then translate 4 on 3 to the right. Okay, finished. Okay, next one is sketch both the standard normal and the fx on the same set of x-axis. Okay, -4 is here. Okay, I'll sketch this one first. Okay, tell me which graph it should be lower or which one is higher. The fx or the standardized normal? Which one is higher? You should know this now. What's the highest point? Highest point is mu 1 over sigma root 2 pi. Okay? So the larger the sigma value, the lower the point, right? The lower the turning point. So which one should get a higher graph? The standardized normal. Because the other one got a standard deviation 3, so should have a lower graph. So I will have this graph first for fx. Well, it's symmetrical at the point 4. Okay, so something like that. And then I have, this is fx. And then I will have normal distribution, which is like that. That's the Z normal. Okay, this point is 0, 1 over square root 2 pi. And for this red graph, this point is -4, 1 over 3 square root 2 pi. Okay, next one. Okay, now come to the serious part of how do we use this to calculate. Okay, the height of the young woman are normally distributed with mu and standard deviation of 160 and 8. Find the percentage of the woman who got the height between 152 and 168. Okay, let's say that first. Let X be the height of the woman. And you know X is normally distributed by 160 and 8 squared. Okay, that's the notation. Okay, there's two ways to do it. You have to think. 168 and 152. That's how many standard deviation away from the mean. If that's a non-calculator question, you will think about how many standard deviation away from the mean. Mean is 160. How many standard deviation away? 1 each side. Okay, 1 each side. So the probability of X in between that is actually 1 standard deviation away. That's 68%. You can have a think that's exactly 1 standard deviation away from each side. That's 68%. But this is no working mark. If that's a 2-mark question, there's no working mark. So what is actually the working mark? Okay, the actual working mark. So there's only 2 things can be tested on. Well, not only 2 things. It's the Part 1, Part 2 exam, right? If it's a Part 1 exam, you need to change it to standardized to Z normal. Okay, to Z normal. Change it to standardized normal. If it's a CAS question like section 2, you just use your calculator. I'll show you how to use the calculator later. But for now, I need to change it to Z. I can directly see that's a 68%. But if it's a 2-mark question, you can't get the method mark. There's no method mark for you. So the method mark will be probability. Okay, 152, back to the Z. What I can do is 152 minus the mu divided by the standard deviation. Okay, X will become the Z because now you talk about the Z normal. Okay, in between those 2 values is equivalent to 2 values on the Z normal. So I will change that to Z normal. So I also change that to Z normal. That's 168 minus 160 divided by 8. So what you have now is minus 1 to 1 for a Z normal. That is clearly showed it is 1 standard deviation away from the mu. Okay? Everyone knows standardized is 0, like the mu is 0 and standard deviation is 1. So exactly shows that it's 1 standard deviation away. And now you can say that's 0.68. Okay, 0.68. Okay, the next one is in between those 2. I'll say 168 and 184. That's the probability. Okay, 168 minus 160 is a 8. 8 divided by 8 is a 1. And go back to Z normal. And 184 minus 160, get a 24. 24 divided by 8, you have a 3. So it's in between 1 standard deviation and 3 standard deviation. Okay, it's in between 1, 2, 3. Okay, 1, 2, 3. So if you go back to this page, okay, from 1 standard deviation to 3 standard deviation, okay, 1 standard deviation is here, 3 standard deviation is here, is 13.5 and 2.35. Okay, is this area here. Is this area here. Okay, from 1 to 3 standard deviation. Start from 1 standard deviation, stop at 3 standard deviation. Is there. So it's 13.5%, 2.35% adding together. Okay, so I have 0.135, 13.5, 2.35, 2.35%, 13.5%. You're just adding those two numbers together. 0, 1, 5, 8, 5. Okay, that's how we find that. Okay, greater than 176. So probability that is x greater than 1, that's the probability of z greater than 2. Minus 160, you got 16. 16 divided by 8, which is 2. So greater than 2 standard deviation. Okay, greater than 2 standard deviation. Okay, let's go back. Greater than 2 standard deviation is 2.35% plus 0.15%. 1, 2. 2.35, 0.15. Okay, 2.35% plus 0.15%. That is 2.5%. 2.5%. If it's less than 136, probability x less than 136, that's the probability z less than minus 160, 24. 24 divided by 3 is minus 3. Is less than negative 3 standard deviation. Okay, negative 3 to the left hand side. That is 0.15%. That is 0.15%. Okay, remember the shape. Okay, on the left of that side. 3 standard deviation away, 0.15%. Let me finish up the B part, B and C part. Okay, one minute. It's 65%. 65%. I want interval. That's 1 standard deviation way. Okay, that's exactly 1 standard deviation way. So you have 152 to 168. Okay, that's 1 standard deviation way. That's the height, cover 95% of your height. Okay, when you see 95%, that will be 1 standard deviation way. Okay, find the highest of the 16% of all the possible heights. Have a think of, yeah. Oh, sorry, 2 standard deviation, yes. So that's 1 standard deviation. If you have that by 8 again, it's 162. And then you sub that by 8 is 144. Okay, 144 to 168. Yeah, 2 standard deviation way. For C, I'm not giving you the answer now, but I want you to go back to this graph. Okay, have a think about where is 16%. Okay, find a special area. Okay. Can you find the area approximately 16% on this graph? Okay, just I have like 8 different values, like 4 different values. Can you by adding some make a 16%? Okay, have a think about that question. Okay, that's why this graph is helpful. Okay, I will start from that question tomorrow.